All right. Hi, I'm Amy Miller. I am a PhD student, and today I'm going to tell you about a novel method for detecting marginally resolved star clusters. And this is in collaboration with my advisors, Maria Rosa Choni, and also Richard D. Grice, as well as Mark Krumholtz, Elizabeth Latta, Zachary Slepian, and the VMC team. So to start off, I'm going to show you the fundamentals. So here, starting on the left in small length scales, we have embedded star clusters, and then moving to the right to larger length scales, we have stellar associations, stellar complexes, and then on the right, a gas-rich galaxy. So the point here is that stars do not form in isolation. They form in correlated clustered groups. And small star clusters are the building blocks. So that is the focus of my project. I study small young star clusters in the Large Magellanic Cloud. And to study them, we need near-infrared data. So I use data from the VISTA survey of the Magellanic Clouds, the VMC survey. So you'll hear more about the VMC survey in Science tomorrow, so I'll just briefly talk about it. So the VMC survey has coverage in YJKS, and there are 110 tiles in total. Each tile covers an area of 1.8 square degrees. And you can see up here on the left, 68 tiles cover the LMC, and then the rest of the tiles in red cover the Magellanic Bridge, the Magellanic Stream, and the SMC. So today I'm going to focus on the LMC, and just for reference, the resolution of the data is about 1 arcsecond, which corresponds to 0.24 parsecs at the distance of the LMC. So now I'll briefly mention two previous studies of young stellar systems in the LMC using the VMC survey. On the top left, we have a map of young stellar structures across the LMC. I made this using resolved upper main sequence stars. And then on the top right, we have a study of one VMC tile. Here, upper main sequence stars and pre-main sequence stars were identified via residual VMC color magnitude diagrams. So these two studies used resolved stars from PSF catalogs. So they were limited by the resolution of the images and the limitations of the PSF catalogs. So they could not confidently identify the smallest, most embedded star clusters in the LMC. So previous LMC VMC cluster studies could confidently detect and study star clusters from a scale of about 10 parsecs to 1 kiloparsec. So what about this smaller length scale? What about the sub-parsec to 10 parsec scales? And we are interested in this scale because this is where a lot of young clusters live. So the typical radius of embedded star clusters in the LMC is about 1 parsec. So we would like to be able to find these guys in the VMC image. But due to the resolution of the VMC data, many star clusters in this size range are marginally resolved, meaning we can resolve the cluster core, but we cannot resolve every individual stellar member. So how can we find these guys in the VMC images? Well, let's look at what previous people have done. So I'm focusing here on studies in a similar resolution and distance range as the VMC data. So at the top, embedded clusters in the LMC with VMC data. So these clusters were found in deep KS images by eye. And then star clusters in M31 and M33 with HST data. So these star clusters were also detected by eye, but using a crowdsourced approach. So they had thousands of people looking at these images and classifying star clusters. So marginally resolved star clusters in our distance and resolution regime have previously been found by eye. But what if we want to apply a more objective detection algorithm? And furthermore, we also have a large data volume, so this drives a need for an automated method. So how can we automate this? Well, first we can define the objects that we're looking for. So on the top left, we want to find clusters that are young, bright in KS, and multistellar structures that are coeval, and more extended than the PSF. And I'm showing two examples at the bottom right. And we are armed with VMC images and the PSF catalogs. So how can we automate this? Well, we can make residual images of deep KS images by removing point sources identified in the PSF catalog. Then the leftover objects should be star clusters, clumps of nebulosity, background galaxies, etc. But there should be a large decrease in the number of objects we detect in the image. So I'm going to tell you now how we did this. I'm going to go through the pipeline, and then I'm going to demonstrate the pipeline on the busiest VMC tile, and then I'm going to discuss the isophote detection that we applied. So the pipeline. Here's a schematic of the data flow of the pipeline. At the top left is the key, so white parallelograms represent input data, pink rectangles represent processing steps, and then blue circles represent input-output generated in the pipeline. So starting in the gray area is stage one. So first we download the deep KS tiles and confidence maps from the VSA. And then we apply CASU's nebulizer software. And then we estimate the background, the spatially varying background and noise. And then we find isolated stars and fit PSF models to them. We save those PSF model parameters. Then we remove and mask stars from the image. And then we have the residual KS image, and stage one is done. Then moving on to stage two, we have the residual image, and we do our initial isophote detection. And then we perform photometry using deep YJKS images that are just the regular images, they're not residual images. And then we perform the photometry, and we have an initial selection where we reject objects based on their morphological parameters and also their photometry. Then we have an initial candidate list. So now I'm going to talk to you in more detail about some of the aspects of our pipeline. And first, I'd like to tell you about the challenges of modeling the PSF in VISTA images. So VISTA's fundamental unit is a paw print shown here on the left. So it has 16 separate detector images. And then 6 of these paw prints are mosaicked to form a tile that covers the full range of area in that region of sky. And now the VMC KS paw prints and tiles. So KS paw print is the sum of 5 dithers shown on the top left. And then 6 of these are taken in one epoch and then mosaicked to form a regular tile shown on the bottom left. And then to form the deeper images, the deepest images, all good epochs are stacked to form a deep paw print. And there are 12 or more epochs in KS. And then 6 deep paw prints are mosaicked to form a deep tile. And we want to use the deepest images so we can find the faintest objects. But the PSF of these deep mosaic tiles is very complex. And that is because each detector image has a different PSF. The PSF varies across each detector. Each paw print has different observational conditions. Stacking affects the center of the PSF and the PSF shape. And so tiles potentially have over 100 different PSFs. So now I'm going to describe how we do the PSF modeling and how we track the variation. So the code finds isolated point-like sources, and then it fits 3 analytic PSF models to the sources. So a 2D rotated Gaussian, a 2D rotated Moffett, and a compound model, which is the sum of the Gaussian and the Moffett, and then it saves the model parameters. And on the right, I'm showing you the mean PSF width across one tile with the Poisson error noted on each grid cell. And then looking at the color bar, we can see that the mean PSF width in this tile varies from about 2.4 pixels to 3.2 pixels. So this tells us that indeed the PSF variation is an important aspect here. So we need to track it, and we need to deal with it if we're going to use these PSF models to remove stars from the image. So now I'm going to describe how we use the PSF modeling to remove and mask stars in the deep KS images. So first we remove Milky Way stars, and we do that using a Gaia and BMC cross-match. Next, we remove stars iteratively in magnitude bins from bright to faint. And then for each star, we create a cutout and we segment and deblend. Then we classify the star as saturated, bright, or faint, and then we remove based on that classification. So for saturated stars, we mask them. For bright stars, we mask the brightest pixels and remove the outer PSF with a PSF model. And then for the faint sources, we just remove with a PSF model. So now I'm going to show you an example of each of these. So this is a saturated star. We make a cutout, we segment and deblend, and then we replace those pixels with zeros. And then a bright star, we make a cutout, we segment and deblend, and then on the third plot on the top, we mask the brightest pixels, so the pixels in the middle in black, and then in the white area, that's where the PSF will be fit. And then 4 options for the white area are looked at: a tailored Moffett, an average Moffett, a tailored compound, and an average compound model. And then the code chooses which option that minimizes the error. And then on the bottom right are shown the best fit residuals. So the star is then replaced with those residuals, and the star is removed. And then for a faint star, we have a cutout again, and then we segment and deblend it. And then in that purple area, we have, again, the same 4 options of different models. And we choose the option that minimizes the error. And then we replace that star with the best residuals, here shown on the bottom right. So now I'm going to demonstrate the pipeline on the busiest VMC tile. So on the top left, you can see an RGB YJKS image of this region with 5 prominent star clusters and star forming regions. And then in the middle, the deep KS image. And then on the far right is the deep KS image after applying my image processing. So now that we have the residual image, we can do the initial detection of objects, and we do this via an isophote detection. So we apply isophote contours at a level of 5 sigma, and we find 1,500 initial objects in this image. Now compare that to applying this detection to just the regular deep KS image. There are 50,000 initial detections there. So using my processed image, there's a 97% reduction in detected objects in this image. And I'm also plotting here some embedded cluster candidates that were found by eye in red, and we detect 95% of these embedded cluster candidates. And now here I'm showing you a zoom in of a region of 2 star forming regions, so you can better see the morphology of these isophotes. And the good thing about this isophote detection is we can study the structural parameters of our detections in detail. So we can study the area, the size, and the perimeter, and we can use these structural parameters to cull spurious objects. And that's something I'm working on right now. And then using the isophotes to compute photometry to remove spurious objects. So we compute the YJKS photometry of these detections. And here I've plotted on the left a color-color diagram, and I've plotted in black probable background galaxies, in green isolated stars, in red the results of the 5 sigma isophotes, and then in blue the embedded cluster candidates. And then on the right, I've plotted a color magnitude diagram with the same color scheme. So something I'm working on right now is using the resulting photometry to cull spurious candidates. And the spurious candidates that we want to cull are poorly subtracted stars, image artifacts, background galaxies, and also blended stars. And so now I'm going to just read a summary. So we developed a pipeline to remove stars from deep KS images to detect marginally resolved star clusters. We detect 1,500 objects in the busiest VMC tile, and we reduce the number of initial detections by 97%. We detect 95% of embedded cluster candidates that were found by eye in the same region. And the next steps will be using the photometry and isophote parameters to remove spurious detections, and then separating the 5 sigma isophotes into higher sigma objects to separate larger star forming regions into smaller star clusters. And finally, process all of the 68 VMC KS images with our pipeline.